Good morning, ma. Yes. Yeah. So in the last class, we have seen about mathematical induction. At the end, what is the motivation or the intuition behind this mathematical induction? It is basic implication, right? We have seen P implies Q. If we have, how we can prove P implies Q is always true? How we can prove? If we avoid the condition that whenever P is true, Q is false, then only it is false, according to the truth table which we have seen earlier. So if we avoid that case, then we can claim that P implies Q is true always. So it is a tautology and it is universally acceptable. This is what we have seen. So now, uh, how we can by using this particular what you call property, like P implies Q is true, then like whenever P is true, Q is also true. If you prove, that is sufficient to claim that P implies Q is a tautology. This is the basis for mathematical induction. So first basic step we will be doing for n naught. Whenever n value is n naught, okay, n naught, for this we will try to claim that f of n is true. Whenever n value is n naught, then f of n is true. This is the basic step. Then in the induction step, we will assume that this one P is true. What is P? F of k. F of k or P of k. That is true. This is the assumption. Whenever this is true, if we show that Q is also true, then it is sufficient to claim that P implies Q is tautology. So what is Q here? F of k plus 1. F of k plus 1 is Q here. So if you claim that whenever it is true, f of k is true, then f of k plus 1 is also true, then we can say that f of n is true for all the instances of n where n is greater than or equal to n naught. Okay. In most of the cases, you might have seen that n naught value is 1. But there can be other cases where n naught is some other value, okay, other than 1. And some examples also we have seen. This is trivial example, 1 plus 2 plus so on, n is equal to n into n plus 1 by 2. Basis step and induction step we have seen. Next, coming to this particular example, here a1 union a2 union a3 union so on an whole complement is equal to a1 bar intersection, a1 complement intersection, a2 complement intersection, a3 complement so on an complement. That is what the statement. How we could able to prove is, whenever we have only one statement, this is the basis step. So one set, if we have, if you complement it, if you apply union or intersection, there won't be any difference. Why? Because we are having only one set. So basic step is over. Next, say I we will assume that for P of k it is true, and for P of k plus 1, how we could able to prove is, LHS side we will be having all the k plus 1 number of number of sets, and we will be having whole complement here. Okay, this is whole complement or whole bar. Now, according to De Morgan's law, what we can say is, this can be first of all, as this follows associativity, we could split it like this has one set, this has another set. Ak plus 1 has one set, a1 to ak has another set. Then we could apply a whole complement by using De Morgan's law. We could divide it like this: a1 union a2 union so on ak whole complement intersection ak plus 1 whole complement. Similarly, we could divide this further up to a k minus 1 and a k, and again we can apply De Morgan's law. Then we could able to prove that it is a1 complement intersection, a2 complement intersection, so on a k plus 1 complement. Then we can claim that p of k plus 1, p of k implies p of k plus 1 is a tautology. Why? Because we are avoiding the only possibility where we will be getting false, that is Whenever p of k is true and p of k plus 1 is false, that we are avoiding here. That we are avoiding in the sense we are proving that that will not arise. So it can be claimed as tautology. So by using this particular mathematical induction, we could able to prove p of n is true for all n greater than or equal to n naught. In this particular case also, n naught value is 1. Okay. Next, we have seen about factorial, right? This one or yeah, another one. Yeah, p of n factorial is greater than or equal to 2 power n minus 1. This is what we have to prove. For that, basic step we have seen like for 1 factorial, it is greater than or equal to 2 power 1 minus 1, which is nothing but 2 power 0. So 1 factorial is greater than or equal to 1. So it is true for basic step. Next, in the induction step, what we have to assume, p of k is true. Then p of k plus 1, which is nothing but k plus 1 factorial. This can be written as k plus 1 into k factorial by definition. So k plus 1 into 1, we know that we have assumed that k factorial is already greater than or equal to 2 power k minus 1. So just we substitute here, so that k plus 1 into k factorial is greater than or equal to k plus 1 times 2 power k minus 1. Then again 2 power k this k plus 1 can be uh, claimed as greater than or equal to 2. Why? Because k value is minimum 1. So k plus 1 can be considered as greater than or equal to 2. Again for this, with respect to this, okay, with respect to this k plus 1 times 2 power k minus 1, this is greater than or equal to this particular one. Okay. Next, and here 2 into 2 power k minus 1, that it is nothing but 2 power k. So we can claim that k plus 1 factorial is greater than or equal to 2 power k. So it is true for p of k plus 1 as well. So we can consider p of k implies p of k plus 1 is a tautology, and we can say by mathematical induction, this holds for all the values of n. N factorial is greater than or equal to 2 power n minus 1 for all the values of n greater than or equal to 1, according to mathematical induction. Okay. Are you having any doubts so far? Yes. Any doubts, man, so far? Yes. Please respond, man. Yes, Manav. Okay. Next. Yeah, this is important and useful concept. Try to understand here. Suppose I wanted to write, don't read whatever the content present, just I will show you when to see. Okay, I will tell you when to see. Now let us consider, we have to um, calculate square root of some number. Okay, n will be given and you have to give the output as a square root of n. This is what the program you have to write. In general, what you will how you will write in C or C++ or in Python, you will be using a built-in function called square root. Yes or no? Sqrt of n you will be using by using math module or math.h in C or some built-in module. You will be using square root, isn't it? Similarly, I wanted to have a program which will take n and it will give n square. This is what the requirement. N square in the sense, let us assume like square root of n, we are having another function called square root square. Okay, sqr of n, which will give square of the given number. Okay, this is what my assumption. Now what will be inside this square function? What will be inside this square function is, let us consider we are having 5, or you consider some big number like 153. Okay, 153, we have to multiply this with 4. Okay, or you consider just 2. 153 we have to multiply with 2. then we can do this by adding 153 with itself. Yes or no? Yes. Yes, please respond. Yeah, if you be interactive, then delay will be reduced. Yeah. So here 153 we have to multiply with 2. This is what our requirement. This can be done by adding 153 to itself. Similarly, 153 multiplied by 4. This is what we have to do. This can be done by adding 153 to itself for how many times?
Four times.
4 times. Like that, what is our requirement is 153 square we have to calculate. So how many times we have to add 153 to itself?
153 times.
Yeah, 153 times. That is one way of getting our required value. Okay, of course we could perform multiplication, but uh, I can say internally multiplication will also be done by the computer as a sequence of additions only. Okay, how multiplication will be it will not perform like what we will do when we multiply, like 153 multiplied by 4 means 4, 4 into 3, 4 into 5, 4 into 5, 1, like that. It won't multiply. Why? Because again 4 into 3, how it has to perform? Try to understand the intuition here. 4 into 3, how it has to perform, how it will come to know. 4 into 3, 4 into 5, how it will come to know. Let us consider 153 multiplied by 14. Now how we have to do? 14 multiplied by 3, how computer will come to know 14 multiplied by 3 is some what is it, 42? How it will come to know? That again will be performed based upon the sequence of additions. By performing sequence of additions only, multiplication will be performed in any computer, that you remember. Similarly, of course, as context is there, I'll tell one more point. Like division will also be done by performing sequence of any answers?
Subtraction.
Yeah, sequence of subtractions. In the case of GCD also, you might have observed. You could get that. Yeah, yeah. Coming to the point, square function we have to define. 153 multiplied by 153 means so 153 times we have to add a number to itself. So what we will do is we will be defining a function like this. Now you consider this function. Here we are saying for this particular a, the number is a, we have to calculate the square. So a we have to add to itself how many times? 153, a number of times. Like 153 we are having a, and for that we are initializing two values. Okay, two variables c and d with 0, and d is the counter actually. Until d becomes a, we have to repeat. What we have to repeat is every time we will be adding a to the sum. Let us say sum is c. Every time we will add to the sum. So first time we will initialize c with 0, so we will add it to 0 itself. So one time we have done c plus a. Next, second time again a value we have to add it to existing c, existing sum, that is c. So c is equal to c plus a. This is what we will do. Then again we will be counting. We have to count. So d value will be incremented by 1. This will be repeated until d becomes a. That means until the count becomes a, it has to be repeated. Whenever d becomes a, we will be returning c value. What this c contains? Just the sum. Okay, whatever the sum we will be calculating. So finally we will be getting the square of the given number. This is simple function. Now, is this code correct or not? This is the question. Yeah, any answers? Will this code will gives square of the given number or not? Always. That's what my question. Yeah, if I give 4, will it give 16? Yes. Like that 16, if I give 256, it has to. So 16, every time it will be adding. Okay, here we are not considering this code with respect to any programming language. So you no need to worry about what is the range of the variables and all. Just C, D, A are the are some of some variables. We no need to worry about the type and what you call range of these variables. So always it will count whatever the number we will give accordingly. Those many number of times it will add. Okay, if you give positive number, then definitely we could able to get square of the given number. If you give negative number, then there is no guarantee. Why? Because it will not become D will not become negative at any time. So D will not become A. If A is negative, this will not give square, but if A is positive, definitely it will give. Yes or no? So that is just an consideration. Yeah. Now, how we could able to prove that this particular code will always give square of the given number for all the positive numbers, whichever we give, for all those numbers, for all those integers, we can say all those positive integers. How we could able to prove that this function will return square of the given integer? Yeah, any answers? Yeah, any answers, ma, for claiming that this function will give always what you call this? Yes, please respond, ma. uh, yeah, I think you have got the question. At least have you understood the question? Yeah, for multiplication, what you call, for negative numbers, it will not work. Yes, of course. Did you understand the question? Yeah. Now, how we could able to prove is we will be giving certain condition. Okay, let us assume a certain condition. This is a C. Okay, some condition we will be giving, and this particular condition is true before this particular loop starts. Okay, here we are using loop, right? While condition and some statements we are using in this particular before this loop starts, this condition is true. Whatever the condition we give, that is true. And after termination of this loop, this condition is true. And for each iteration, that is yeah, this particular loop can run for 4 number of iterations or a number of iterations, right? A times this loop will be repeated. For all those iterations, this condition is true. That is, before starting of the loop, it is true. Before starting of each iteration, it is true. After completing all the iterations, it is true. Then this particular condition, we call it as loop invariant. I'm repeating once again. Loop invariant is nothing but before starting of the loop, this particular this is a condition. Actually, loop invariant is nothing but a condition. Before starting of the loop, this condition is true. Okay, that is preliminary check. Next, while running the loop, for each iteration, okay, before starting of each iteration, the loop invariant is true. And after completing all the iteration, the loop invariant is true. Then we can claim that whatever the function we have defined by using this loop will give always correct answer. Did you understand what I am saying? I'll show you examples. Don't worry. Just if you understand the definition, we'll go to the examples and all. Yes. Shall I repeat?
Sir, please repeat it.
Yeah. See, we will be giving a condition called loop variant, and by using this loop variant, we will claim that this function will give always correct value. Okay, always correct value. This is what we are saying as loop invariant. What is meant by loop invariant is it is a condition like a is equal to b, let us say this is a condition, or a is less than or equal to 10, this is a condition. Like this, some condition we will be giving. This condition is true before starting of the loop. So here we will check. Okay, here we will check and this is true. And after completing this loop we will be checking and this will be true. And while iterating through the loop, before each iteration this condition will be checked, and then also this condition is true. Then we can say this is loop invariant. And by claiming there exists loop variant for a loop, we can claim that that code is correct. This is the method, like which we have discussed with respect to mathematical induction. P of k is true, P of k plus 1 is also true. Whenever P of k is true, then we can claim that for all the values of n it is true. Similarly here, what is the method is loop invariant is the condition, like a is equal to b, or a less than or equal to 10, or a plus b is equal to 10. Like that, some condition we will be giving as the loop invariant. So according to the before starting of the loop it is true, by iterating before starting of each iteration it is true, and after completing all the iterations also, that is after terminating the loop also, that condition is true. Then we can say it is loop invariant. By claiming there exists loop invariant, we can say that code is correct. Okay, now coming to this particular example, if you understand up to some extent, that is also sufficient to understand the example. If you see the example, then you will get more clarity. Yeah, now we can say there exists a loop invariant such that like we will be having sorry, just a second. Yeah, okay, see here, the loop invariant here is Cn is equal to a into dn. This is what loop invariant. What does it mean? Cn is nothing but sum after n times. Okay, sum after n what you call iterations. A into a is the given number, and dn is nothing but how many what is the count. Okay, how many number of times we have repeated, the loop. This is what the statement we have to prove. Okay, this we are claiming as loop invariant. How it can be loop invariant is before starting of the loop, what is the value of n? What is the value of n? That means how many times we have repeated before starting of the loop, how many times we have repeated the loop. Just zero, right? So n value is zero. How many times we have multiplied a with itself, a with sorry, how many times we have added a with itself? Zero times. So n value will be zero. C zero. Next, dn is nothing but how many number of times? It is nothing but almost n. So it will be zero. Now c0 value is 0 and d0 value is also 0. Then a into 0 will be 0 itself. So c0 value here is 0 we have initialized. D0 is 0. So if you substitute here, is it satisfying this condition or not? This particular loop invariant or not? Before starting up the loop.
Yes, sir.
Yes. Next, while iterating through the loop, after before every iteration, let us check. Like after two iterations, n value becomes 2 and dn value will be, that is d2. D2 value will be 2, right? After two iterations, that is before third iteration, dn value will be 2. Now a into 2, what we will be getting? 2a. So that is what we will be having in Cn. Yes or no? C2 will contain 2 into a. Yes or no?
Yes, sir.
Yeah. So like that, after k iterations also it is true. Why? Because after k iterations, k into a will be the value of cn.
Yeah.
Okay, and that is what we will be getting the sum. So this is the loop invariant. After completing the loop, what will be the value of dn? If you answer this, you have understood correctly. After completing the loop, what is the value of dn? Yeah, capital A. The value of dn is a. Why? Because n number of times, in the sense a number of times this loop will be repeated. The in at that particular time, what is the value of cn?
A square.
A square. That's it. So are we able to satisfy this particular condition always? That is in all the three particular what you call places.
Yes, sir.
Yes. So can we consider this as the loop invariant?
Yes, sir.
Yes. So we can claim that this particular code is correct for all the values of a. This is what the procedure. Let us see other just you can find this one in net, and you can find several other examples as well. Just I will go through one. See, a loop invariant is a condition that is necessarily true immediately before and immediately after each iteration of the loop. Understand? Before iteration, in the sense before first iteration also, before every iteration also, and immediately after each iteration, in the sense it is nothing but after all the iterations also it should be true. Understand? It is other way of saying, I have divided into three steps, like before starting up the loop, while iterating, before each iteration, and after completing the loop. Like that I have divided. This can be consolidated like this: before and uh, after, immediately after each iteration of the loop also this condition is true. So for example, we are having the loop like this: integer j is equal to 9, and we are initializing I value as 0, and I is less than 10, I plus plus, and the statements inside the loop is only one statement, j minus minus. Now we have to give loop invariant, that is one condition which one is true for true before starting and after starting as well. Now I am claiming that I plus j is equal to 9. Let us see before starting of the loop, like before starting this particular statement, what is the j value? What is the value of I plus j directly? What is the value of I plus j? 9. Of course it is not completely correct. Why? Because it is a syntax, what you call a programming language specific, this particular syntax. If you convert this into algorithm, we will not be having integer I is equal to 0 here. Somewhere before only we should declare I value. So we can assume that I value is 0, and now I plus j is 9 before starting up the loop. Next, after two iterations, what will be the value of I?
2.
2. Now what will be the value of j? Two times we
7.
will be decrementing, 7. So I plus j will be
9.
9. uh, at the end of the loop, what is the value of I?
9.
Okay. Next, what is the value of j?
0.
0. So I plus j will be
9.
9. So like that we can claim that this condition is true always. Okay. And one more time I am repeating the important point. It is specific to the programming language, this particular syntax. But if you consider pseudocode, we will not be having I plus plus functionality as you could do it in C. In C, what will be the value of I after completion of the loop? Can anyone able to say? After completion of this loop, what will be the value of I in C? Yeah, 10. But it is not in the case of pseudocode, that you keep in mind. So I value will remain at 9 only. Why? Because we will our intention is to repeat the values from I value from 0 to 9. That's it. For our convenience, we have written as I less than or equal to 10, and according to C syntax we have written like this. But if you convert it into this algorithmic perspective, we will be having I value as 9 only. That you keep in mind. I hope you understand what I am saying. Yes, Jian? Yeah. So this is one of the examples of loop invariant. There exist several other examples as well. For I don't know whether you are familiar with the selection sort, bubble sort, insertion sort, quick sort, these kind of things. Are you familiar with this? Just these are other algorithms. Okay, if you don't have knowledge about it, then you leave it. Just you stick to this particular example, these two examples which we have seen in this and this one. Okay, so loop invariant is very much important to claim that whatever the program you have written, that is true. And one more point I wanted to add here. I will ask one question, try to answer. What's the difference between the condition, loop condition, and the loop invariant? Hmm. Is there any difference between loop condition? We will be having condition, right? Like I less than or equal to 10. Is there any relation between the condition and the loop invariant? Yeah. Are those two same or not? Just you answer this. Hmm. Loop invariant and loop condition. Yeah, those are not same. Why? Because loop condition will be failed after the loop ends. So it is not same as loop invariant. But loop invariant is true before starting of the loop, while running the loop, while running in the sense before each iteration, and after completion of all the iterations. Also, the loop invariant is true. That's the difference between loop invariant and a loop condition that you keep in mind. I think here also they might have mentioned. I think you can find, if possible I will share it in slides. Yeah. Okay, this is about mathematical induction, and afterwards we these are methods of proof. So we can say in broad way, methods of proof. First we have seen modus direct proofs by using facts and all. Next we have seen by using modus ponens, that property. Whenever p is true, p implies q is also true, then we can claim that q is true. That is modus ponens. Then indirect proof, that is in order to prove p implies q is true, we can take a negation q implies negation p. If we prove this, then also we can claim that p implies q is true. That is indirect method. Then coming to other thing like proof by contradiction, we have seen, right? Proof by contradiction is nothing but we will assume that p is true. After that we will come to know, we will arrive the conclusion that it is a contradiction. So p is not true, we can claim that negation p is true. That is what proof by contradiction. We have seen one example related to it. If possible, in coming classes we will see other examples related to proof by contradiction. Proof by contradiction is very much important. And coming to implication, p implies q is true whenever p is true, and true is also true if you prove that p implies q is tautology, then that is universally acceptable, and we can say it as rule of inference. And based upon this we have defined mathematical induction, and several examples we have seen. Next, coming to loop invariant. What's the difference between loop invariant and loop condition? And this is this loop invariant is used to claim that the given code is correct. Okay, this is what we have seen about methods of proofs. Are you having any doubts? Yes, any doubts so far in methods of proofs? Okay. Okay. Now let us see. We have seen like what is meant by set and what is meant by sequence as well. What is meant by set? Set is nothing but a collection of elements, collection of objects or elements, we can say as set. And uh, yeah, how sequences can be derived from set? Yeah, how sequence can be derived from set? Like we'll be having alphabets as set. Okay, all the alphabets as set. From those, if you get any word, that is a sequence. Yes or no? Sequence is nothing but string also can be considered as sequence. Why? Because ABC is different from in general, ABC is different from CBA. So we can consider sequence is nothing but will be deriving from set elements only. Okay, and coming to the possible types of combinations that we can have from set is like we can have sequences, okay, in any order, and those elements can be in any order, and duplicates are allowed. And in any order we can take, but duplicates are not allowed. And duplicates are allowed, but whatever the order we are taking, that matters. That is, ABC is different from BCA. BC, what you call BCA. Okay, like that. If order matters, then it will come into third category. And if duplicates are not allowed and order matters, then that is fourth category. These are several ways where we could able to create sequences from set. I hope you could able to follow. Yes.
Yes, sir.
Yeah. Now let us see some of the examples where we will be generating sequences from set. Like you consider, these are all examples. I will consider one of these. Like you consider four numbers. Okay, in general, how many numbers will be having? 10. So 10 numbers. What are the possible numbers? Like 10 digits will be having, we will be having, right, 0 to 9 for each digit. 10 places we will be having. In all those 10, we'll be having how many possibilities? Like for this we can have 10 digits we can have for this 10, for this 10, like this 10 possibilities we can consider for all these 10 digits in general. But if there exists some restriction, like if 0 is there, it cannot be considered. Then we should we will be having only 9 possibilities for this, and for all the remaining 9 places we will be having 10 possibilities. Yes or no? Yes. Yeah. Now you consider this four numbers example itself, how we could able to count how many number of possibilities. Like instead of that, let us consider number plates in for bike. Okay, in general we'll be having four numbers, right? Yeah, excluding that some state code and other codes. Just last four numbers you consider. Okay, four digits. So for this we can have any of the 10 digits. Okay, any one of the 10 digits for first one as well. Yes or no? For second one also same, for third one also same, for the fourth one also same. So for four places, for four digits, we are having for the first one 10 possibilities, and for second one also 10, third one also 10, fourth one also 10. So how many possible numbers we will be having for what you call this one, for bike number with four digits? Yeah, 10 power 4. Gian, why triple four nines? Is there any reason? All zeros. Okay, number plate cannot be zero. Yeah, okay, fine. So now like not all can, yeah, all cannot be 0. That one possibility we can exclude with respect to the application. Okay. Now consider here four only two digits if we have, then what are the possible numbers? Possible numbers are, here we will be having 10 possibilities for this 10. So 10, how many possibilities for two digit numbers? How many two digit numbers will be there first of all? Yes, how many two digit numbers? 100. Now starting from 00 to 99, so total 100 numbers will be there. How we could able to count that is, for the first digit we'll be having the possibilities as 10, for the second digit also 10, 10 multiplied by 10, so we will be getting 100. Okay, this particular one we can say it as principle of counting, multiplication principle of counting. Okay, let us see, like we are having two tasks we have to complete in a sequence. Okay, t1 we have to complete first, then t2 we have to complete. But t1 can be completed in n1 ways and t2 can be completed in n2 ways. Now this particular sequence can be completed in how many ways? Is n1 multiplied by n2. Is this clear from the intuition which we have seen? Yes. Yeah. Uh, Now, are we considering duplicates or not in this particular one? Are we considering duplicates? Yes. Why? Because same number of what you call, like here we considered 10 digits, 10 possibilities for the first digit, 10 possibilities for the second digit. So, likewise, here n1 ways, n2 ways, n1 multiplied by n2 we are considering. So, here we are considering duplicates, and of course order also matters. Why? Because t1 followed by t2, this is what we are saying, so we are following the order as well. So this is the first example, one of the examples of these four possibilities. Yes. Now sorry, let us consider we are having k number of tasks, t1 t2 t3 so on tk, and t1 can be performed in n1, t2 can be performed in n2 ways, t3 in n3, like that tk can be in nk. Now we have to perform all those tasks in the sequence t1 t2 t3 so on tk. Then how many possibilities we'll be having, in how many ways we could able to do it? Is again by using multiplication principle of counting, like n1 multiplied by n2 multiplied by n3 so on nk. This is what the result. Clear? Whenever we have k number of tasks, then we will be having this result. Yeah. Next, other examples, like 8 character passwords we have to get. First, these are the two restrictions. First character must be a letter. Remaining 7, any character after that can be a letter or number. Okay. Now first character must be a letter. How many possibilities for letter in general you consider? 26. Next, after that we can have letter or number. So number in the sense, for each and every digit, how many possibilities will be having? 10 for digits and 26 for a letter. So total 36 possibilities will be having for each digit. Yes or no? So 36 for this. Like that, how many characters we are having? 8 total. So this is, first one is over, so remaining 7 will be having. All these 7, for all these 7 we can have 36 possibilities. So 36 power 7 multiplied by 26, or according to this n1 n2 n3 so on nk, 26 multiplied by 36 multiplied by 36, like that, so on 7 number of times 36. It is nothing but this one, 26 multiplied by 7 times 36, we will be getting this one. Okay, this is one of the examples. Another one is like one key we have to generate. Okay, it is of length 25 characters, and it can be of numbers and letters and numbers. So for every number we will be having 36 possibilities, including the first one. So 36 multiplied by itself how many times? 25 times. So 36 power 25. This is based upon the multiplication principle of counting. Clear? Is this clear? Yeah. Now other examples also you can go through these examples. I don't want to um, concentrate. Yeah. Now let us see, we are having a set with n elements. Now how many subsets we have to count. Again it is counting, right? How many number of digits we have, how many number of subsets we have for this. This can be um, considered as a power set. What is the power set cardinality? 2 power n. Straight away we can say 2 power n and conclude. But that can be proved like this as well. Another possibility, like we have seen characteristic function earlier. Before I think quiz 1 itself we have seen characteristic function. Yes, characteristic function will define whether one particular element is present in this set or not with respect to universal set. Likewise we can define so fa universal set is this. A is 1 comma 2, then fa is nothing but characteristic function where whatever the elements we have with respect to universal set, corresponding entries will be 1, remaining will be zeros. So 1 1 0 0 0 0, this will be characteristic function. For b 2 4 6, so corresponding digits will be corresponding entries will be 1, remaining will be 0. This is characteristic function. Now you consider how many entries will be having in each characteristic function. Like this particular one, how many entries will be there for any set? 6. Yeah, 6. What is the what are the possibilities for first number, first entry? How many possibilities? 2 possibilities. For the second number, how many possibilities? 2. So if you consider 6 digits, how many possibilities will be having? 2 power 6. How many elements we are having in the set? In the universal set, how many possibilities? Yeah. So how many what you call subsets we will be getting? How many subsets? 2 power 6. That's what we can conclude. It is similar to this application, right? 2 into like n1 into n2 into so on nk. For the first one we are having 2 possibilities, for the second one 2, for the third one 2, like that to 2 power 6. Is it clear? Yes. Yeah. Now this is another application of multiplication principle of counting. Yeah. Next, coming to another type of sequence where we have listed 4, right? Out of those, another sequence we will be considering where duplicates are not allowed, but order matters. Duplicates are not allowed. Now how we can consider this? A is a set with n elements, and we wanted to get a sequence of length r. We wanted to get a sequence of length r. If you consider r as length n plus 1, what will happen, ma? Suppose r value is n plus 1, what will happen? Yes, any answers? This particular property we will be violating. Duplicates are not allowed, right? N plus 1 means definitely at least one we have to repeat. Yes or no? That we will discuss in coming classes in detail. But yeah, anyway, as condition is uh, defined here, I wanted to mention that. Yeah, if you have n plus 1, at least one element we have to repeat. That's what. That's why r value should be maximum of n, so that duplicates uh, are not allowed. That condition can be followed. That's what the intuition here. Now if we are having uh, what you call same like 4 digits, okay, 4 length number we have to form, but for the first one the values should not be repeated. In the sense, for the first one how many possibilities we will be having? 10 possibilities we will be having. For the second one, how many possibilities we will be having? 9. Why? Because it should not, whatever the digit we have placed here, that should not be repeated. For the third one it is 8. For the fourth one, 7. So by considering this, you consider for the first one we are having n possibilities. What will be the second one possibilities? Number of possibilities for the second one? N minus 1. For the third one, n minus 2. Like that, I wanted to get for r length. So what will be the result? N into n multiplied by, yeah, please repeat, n into n minus 1 into so on, so on. I wanted to get result for what you call the length of the sequence is r. I am saying what will be the value? N minus, yeah, n minus, one more time. If the length of the sequence is 2, n minus n into n minus 1, up to that. If the length of the sequence is 3, n into n minus 1 into n minus 2, n minus 2 itself we will stop. If the length of the sequence is 3, I am saying we have to stop at n minus 2, correct? So if the length of the sequence is 5, then up to n minus 4 only we will stop. If the length of the sequence is r, then up to hmm, the length of the sequence is r, then up to n minus r minus 1, it is nothing but n minus r plus 1. Yes or no? So up to this we will be repeating n minus r plus 1. Yeah. Now you consider, is there any relationship with this and n factorial? Yeah, n into n minus 1 into n minus 2 into so on, n minus r plus 1. If you extend it up to 1, if you extend it up to 1, what are the other terms we have to add? What are the other terms? Like we are having up to n minus r minus 1, okay, n minus r minus 1, up to 1 we have to consider. Then those we have to divide, right? Like you consider n value as 9, we are having up to 5, n value as 9, and up to 5 we are having. In order to make this one as 9 factorial, what can be done? We have to multiply with 4 factorial. Yes or no? And we will divide with 4 factorial. Yes or no? We will multiply with 4 factorial and divide with 4 factorial, so that the numerator will become 9 factorial. Now this can be written as, this 4 can be written as 9 minus 5. Yes or no? 9 minus 5 factorial. Yes or no? Yeah. Now I'm saying this one has 9 factorial, this one has 9 minus 5 factorial. What is 9 here? It is nothing but n. What is 5 here? What is 5 here? It is nothing but r. So n minus r factorial. Yes or no? N factorial by n minus r factorial, which is nothing but just one minute. Yeah, n factorial by n minus r factorial, which is nothing but npr. Like this, if we have n elements, and what are the number of sequences which we can form with the length r, that is how many elements we can select without repetition, how what you call how many ways we can select r elements without repetition is nothing but npr. What is the intuition? This is entire thing is intuition. Yes, did you get the point? Yes ma. Yeah, with this I will stop. In the next class we will continue. Okay, thank you ma. You can enter your roll number and can leave. Thank you.